Iron oxide, the ore from which iron to be extracted, is concentrated by roasting or calcination so that water gets eliminated as vapor. Carbonates get decomposed to release carbon dioxide, and sulfide gets oxidized to sulfur dioxide. This concentrated ore is mixed with limestone and coke and sent into a blast furnace to reduce the metal oxide to the metal. Here, coke reduces ferrous oxide to iron, releasing carbon dioxide, as shown in the equation here. This is a combination of two simple reactions. In the first reaction, ferrous oxide gets reduced to iron. Let the change in the Gibbs free energy for this reaction be delta G, FeO, Fe. In the second reaction, carbon gets oxidized to carbon monoxide. Let the change in the Gibbs free energy be delta G, CO. When the two reactions occur, the net Gibbs energy change becomes delta G reaction is equal to delta G CO plus delta G FeO Fe. This becomes spontaneous when delta G reaction is negative. Ellingham diagrams are useful in predicting the conditions under which a metal ore can be reduced to the metal. It gives information to predict the equilibrium temperature between the metal oxide and the metal. If a graph is plotted for standard Gibbs energy change delta G naught against temperature in Kelvin scale, capital T for both these reactions, then it will go upwards for the reduction of ferrous oxide to iron, FeO, Fe, and downwards for the oxidation of carbon to carbon monoxide, CO. From the graph, you can see that at a temperature above 1073 Kelvin, carbon reduces iron oxide to iron, but itself undergoes oxidation to form carbon monoxide. Thus, the carbon monoxide oxidation line crosses the iron oxide iron reduction line and then remains below it. Let us apply this concept to the extraction of iron in a blast furnace. In the furnace, iron oxide is reduced at different temperatures. Iron oxide ore is introduced into the furnace from the top. At the same time, coke is burnt in the lower portion of the furnace, blowing hot air to produce a temperature of 2200 Kelvin. When the coke burns, it produces carbon monoxide and the heat required for the process. The heat produced moves upwards along with the carbon monoxide. The temperature at the top of furnace is lower, and hence iron oxides like Fe3O4 and Fe2O3 get reduced to FeO in different stages. This corresponds to the intersection points in the curves which we just discussed. Let us now see how iron oxides get reduced to iron in different temperature ranges. Between 500 and 800 Kelvin, carbon monoxide reduces iron oxides as shown here. Carbon monoxide acts as a reducing agent since it has a lower negative delta G naught value for the oxidation of carbon monoxide to carbon dioxide than for the oxidation or carbon to carbon monoxide. Thus, in a blast furnace, hematite is reduced by carbon monoxide even though carbon is mixed with it. The equation for this reaction is Fe2O3 plus 3CO gives 2Fe plus 3CO2. In the temperature range of 900 to 1500 Kelvin, carbon monoxide reduces ferrous oxide to iron as shown here. Silica is an impurity. Limestone removes it in the form of molten slag, which is taken out from the bottom of the furnace. The molten iron obtained in this process contains 4% carbon, along with some other impurities like sulfur and phosphorus. It is called pig iron. Pig iron is melted with scrap iron and coke in the presence of hot air to form cast iron, which contains only 3% carbon. It is hard but brittle. Cast iron is heated in a reverberatory furnace lined with hematite, which oxidizes carbon to carbon monoxide to get wrought iron or malleable iron, the purest form of iron. In this process, limestone is added to remove impurities in the form of slag. The metal is removed and separated from the slag by passing it through rollers. Copper occurs in combined state as sulfides, oxides and carbonates. Copper pyrites or chalcopyrites and copper glans are its sulfide ore. Cuprite is its oxide ore, while malachite and azurite are its carbonate ores. Now look at the Gibbs energy versus temperature plot for the formation of oxides. You can see that the line for cuprous oxide is almost at the top, while the lines corresponding to the formation of carbon monoxide and carbon dioxide from carbon are much lower, particularly after 500 to 600 Kelvin. Therefore, it is quite easy to reduce cuprous oxide to copper by heating with coke. However, most ores of copper are sulfide ores, and some of them may contain iron. Hence, the sulfide ores are first roasted or smelted to give oxides. The oxides are then reduced to metallic copper using coke. In practice, the concentrated sulfide ore containing iron as an impurity is mixed with silica and heated in a reverberatory furnace. During this process, most of the iron sulfide is converted into its oxide, which further reacts with silica to form a fusible slag of iron silicate. Copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The molten matte is now introduced into a converter provided with a lining of silica. A blast of sand and hot air is blown into it. During this process, the remaining iron is removed in the form of slag, while copper sulfide is reduced to metallic copper. The metallic copper then melts and sinks to the bottom of the converter. This molten copper is poured into molds. When the molten mass is allowed to cool down, SO2 gas escapes. As a consequence, the copper so obtained has a blistered appearance. Hence, the product is called blister copper. Blister copper contains 98% copper and is refined through electrolysis. Now let us look at the extraction of zinc. Zinc occurs widely in nature in the form of sulfide, oxide, and carbonate ores. Zinc blende is its sulfide ore, zincite its oxide ore, and calamine is its carbonate ore. As can be seen from the Ellingham diagram, the reduction of zinc oxide to zinc occurs at a higher temperature than that required for the reduction of copper oxide to copper. Coke is used for the reduction of zinc oxide. Depending on whether sulfide or carbonate ores used for the extraction, the concentrated ore is either roasted or calcined. The zinc oxide obtained after roasting or calcination is reduced to zinc in vertical retorts. In practice, zinc oxide is powdered, mixed with coke and clay, and then made into small briquettes. The briquettes are placed in vertical retorts that are lined internally with clay bricks. Producer gas is used as the fuel to heat the charge. At high temperatures of 1400 to 1500 degrees Celsius, coke reduces zinc oxide to zinc and itself gets oxidized to carbon monoxide. The zinc metal is distilled off and collected by rapid chilling. The zinc obtained is 97% pure and is called zinc spelter.